Now see, right now I want you to focus. We said, actually, if we just write the plus sign equals 0, we already have perfect formulation of the find volume method. Just for the steady state, we've omitted the time derivative, and we've omitted the source term for a minute. Yeah? But what we've got here is, again, diffusion flux, convection flux, convective flux. So already the full formulation of the discretized find volume method. Now, the first important remark is that you need to calculate these fluxes to assemble the matrix of your find volume method, or to just calculate the fluxes if you're dealing with explicit find volume method. And we will try to do it in a minute. But now, if we've got, right now, please focus because it's one of the most important things about find volume method. If you've got two find volumes, calculating the fluxes for this volume means looping over that, and that phase. Later on, when you will be calculating the fluxes for this cell, you will be looping over that phase. Is it the same flux? Yeah, exactly. It's opposite sign. But apart of the opposite sign, nothing else changes. Like you should have the same velocity, the same U value at the face, and the same surface area. Only the sign changes. So first of all, you can reduce your computational effort by a factor of 2 by simply calculating it once and applying it to the other cell as well. The other thing, most important for the find volume method, is that because of this property, that when you're calculating this flux for that cell, it will be exactly the same flux for the other cell. This one means that the find volume method is conservative. It's conservative in its formulation. What it means is that if you calculate, if you do all the addition and multiplication with infinite precision, so not with machine precision, but with infinite precision of the arithmetics, then the flux that is transported out of this cell will go to this cell. If it's transported forward, it will go to the other cell, etc., etc. And for the whole domain, it works like if you've got some portion of the boundary, where you might have the Neumann boundary condition, so you're introducing the flux, then you have guarantee that this flux will be transported through the whole domain and out of it, because what comes into one find volume will leave the find volume, but exactly the same value and exactly the same amount of this quantity will enter the other find volume, etc., etc. So if you're computing everything with infinite precision, then your scheme is fully conservative. And that's one of the motivations why the find volume method is so popular in CFD, because it has got this property that in CFD you generally want to discretize conservation equations. And if you want to discretize conservation equations, then it's nice to have a conservative scheme, because then it should guarantee that, for example, your momentum, your energy, or something like that will really not change at all. It's conservative in the formulation. obviously you're not calculating everything on the computer with infinite precision. So there are already some round-off errors. If you discretize it to the system of linear equations and you solve the system of linear equations, then also you introduce, you simply solve your linear systems with certain residuals that you accept. So the numerical solution will not be fully conservative, but the formulation of the method is. And Piotr, you said neighbors. Yes, that's right, because now you need to have neighbors to improve your code, because then calculating this flux once means that you can very, very quickly, if you know from the data structure who's my neighbor for that phase, then you can quickly go to the other cell and say, okay, so is the flux that I should assign in the other cell. But to be honest, not only, because right now let's have a look at this diffusion flux. And let me assume for a minute that lambda is constant in your whole simulation. So lambda at phase is simply lambda. We need to calculate this gradient du dn. How do we do that? Well, let me draw it like that. And that's why we need to assume that the values are stored at the centroids, because what you need to do here, if you want to calculate the diffusion flux, you should calculate what's the lambda at the phase. That's something that we know. We know the surface area, but we need to calculate du dn. And how you usually do it is you're using the approximation that du dn at the phase is nothing else as taking u at the neighboring node minus u at, let's say, I is my cell. That's the neighboring cell, divided by, well, L or D. Let's say it's the distance. It's the distance between these two centroids. So we are taking the magnitude of the distance, and that's how you discretize the diffusion flux.
I've been wondering, because the way we calculate the gradient is first order. Is there any method to increase the order? Because in the finite difference method, we just could simply take 3 consecutive points, but here it seems impossible.
The nice feature is because you have started with the differential equation that is second order, but we have integrated that. So the highest derivatives that exist in our formulation right now are first derivatives. We got rid of second derivatives at all. Then if you've got, let's say, for instance, if you've got finite volume method, which is discretized on Cartesian grids, and you're using such a formula to compute the gradient, the method will be of second order. So it's not, so the whole method will be not first order, it will already be second order method. Then I think for non-structured meshes, the problem is the following, that if you take equilateral triangles, then everything is nice, because taking this approximation to calculate du dn is strict mathematically, because then your the direction of the unit normal vector is exactly the same as the direction of this line segment D, and it's proper calculation of the gradient. But what if you've got something like that, then the centroid is more or less here. Here, well, the unit normal vector is in that direction, but the line segment connecting these two centroids is not parallel to the unit normal vector. And by saying that you can approximate dn by this formula is already introducing some error, and that's why it's not very nice for the defined volume method to have skewed meshes. What you're trying to work with when generating proper mesh is to have as little skewness in the mesh as you can have.
For best practices that Piotr just wrote.
So that's something that I think would introduce that your method is not of second order anymore, but it's probably somewhere between 1 and 2. Okay, so coming back to the data structures. Now you see we need to compute this gradient. We need to approximate the gradient somehow. And to do so, when assembling the equation for our find volume, then we definitely need to get the value of the quantity at the neighboring cells. So without the neighbors array, implementation of the find volume method would be like looping over n square possible all the cells that you have in the mesh, and it would be a nightmare from the computational point of view. So you definitely need to have the array storing the neighbors. Well, let me skip that. You would need also some array or a couple of arrays that will represent your boundary conditions. Let it be probably the simplest approach is you need to have some groups saying that at which phases you've got what kind of boundary condition, or the other formulation is generally the find volumes, the same with the find elements. Very, very often you say that, okay, I've got some local node 1, 2, 3, and the global node might be then 7, 3, 4. Let's say these are the local nodes, and the global nodes are 7, 3, 4. Very often you would say that, okay, so between my first and second local node, I've got phase 1. Here I've got phase 2 and phase 3. So the other way of specifying the boundary conditions is saying, okay, I've got the boundary condition at, well, cell 1, phase 1, at cell 7 phase, let's say, also first phase, etc. And you need to prepare such a list of cells and appropriate phases where you want to impose the boundary condition. And you need to know what kind of values you want to impose there. Is there an alternative approach to specify the data structures?
Excuse me, I've got a question, because you wrote down how do we store information about cells, and how looks that array of neighbors and of PCs. For example, when we describe cells, we've got number of nodes that create each cell in each row, and how looks that neighbors and PCs storing just in order.
Regarding neighbors, I would use this concept of the local numbering of the phases. So I would assume that the neighbors that's something that is defined for each cell. So if we've got 9 cells in the mesh, then we would have, again, the array of, 9 rows. Each row represents one find volume. And let's try to focus on our second cell. Then I would say, okay, so here we've got, as we said, we've got local phase 1. So then our neighbor is the first cell. Then our neighbor through the second local phase is third phase, and here 8th cell. Okay, and with the BCs, in this convention, I would say something like that. Well, just imagine that we want to specify the Dirichlet boundary condition here and some other boundary condition here. Okay? What I would do is I would say, okay, so this is like our maybe first boundary condition that we want to specify. That's the second one. Like it's like a well-specified portion of the boundary. That I mean by, so one is a portion of boundary where you would impose one boundary condition, and the second one is something that you want to keep separate, to be able to specify a different boundary condition. What I would do in such a case is I would write that prepare a list of boundaries. I would probably use something like that. Let's say eighth cell. Oh, well, we didn't agree which is first phase, but let's say it's first, second, third. So we need to impose the boundary condition on the fourth local phase. And what is it? It's first type. Okay. Then the ninth cell. Again, well, let's say first phase. Again, first boundary condition. Same here, like, I don't know, third cell, let's say first, second local phase, boundary condition 2, etc. Then you only need to have some data structure that would store information. Okay, what should we impose at boundary condition 1 or 2, etc. What kind of value you want to specify there. And one more remark is what happens in the find volume method if you don't specify the boundary condition at all?
There is a zero flux.
Exactly. See, if it's the boundary of the domain, so you've got no neighbors, you will not be able to go to the neighboring cell. So this flux and this flux will be 0. So for free, without doing anything, you get 0 Neumann condition in the find volume formulation. Is there any alternative way of specifying the data structures? Something that I was very much surprised when I got to know how ANSYS Fluent stores meshes. Can you think of any data structures that would be very, very convenient for the find volume method?
I just know how Fluent store mesh, so
I think it's like we could store directly faces Like all the faces between the cells.
Yeah, exactly. So the alternative way of storing the same information is, let me erase that. The alternative way is, well, we still need to store the nodes, that's clear. Second thing, we store faces, just faces. So what you would need to do for this mesh, so you would need to say, okay, 6, 1 is one face, 1, 7 is other face, 1, 2 is other face, and you need to prepare the list of the whole collection of all the faces in the mesh. Basically, you're not preparing any data structures saying anything about, saying explicitly anything about the connectivity of cells. You only store the collection of faces, and for each and then for each of the faces, what you store is you store the face, let's say 1, 7, and when storing the face, you say which cell is on the left-hand side of the face and which cell is on the right-hand side of the face. Why? Okay, and something that is extremely clear, you need to store IDs of volumes of cells. Why? Because you need to prepare the solution vector. So you need to know how many cells you've got in your mesh. But by storing the faces, what you can do in the discretization is, you see, the discretization of the find volume method requires only calculating the fluxes and nothing else. So you can use this array to go through all the faces and simply calculate the fluxes. Well, and you need to know from the faces which cell is on the left-hand side and on the right-hand side to, for example, calculate this this gradient, but that's it. Something that is very, very difficult to imagine in the find volume method. In find element method, in find elements, you would rework with nodes and elements. In find volume, you can work with nodes and cells, and that's already good, but you can also work with nodes and faces, and that's same good.
I have a question concerning the boundary conditions. So we don't have to impose boundary conditions on every boundaries. Because in the other method, we had to impose those boundaries everywhere, those boundary conditions. And now, let's say that we don't do this, so the solution just adjusts on the boundaries.
It depends how you define the problem. Like, I would say every discretization method has got its so-called natural boundary conditions. And natural boundary condition is something that that results from the discretization method without doing anything. So for the find volume discretization, doing nothing at the boundary means having zero flux. Okay, so maybe it's not properly set in the mathematical sense that you don't have any boundary condition. In the mathematical sense, this would be where you do have zero Neumann boundary condition everywhere here and here. But if you need to specify, let's say, Dirichlet boundary condition, you don't need to, for some portion of the boundary, then you only need to highlight this portion of the boundary and to re-specify it in the find volume discretization. But if you got the Neumann boundary condition at the other part of the boundary, you don't need to do anything. Then I've got a question to you. let's assume that we are working with data structures where we've got nodes and cells, and you need to have the array of neighbors. If you're importing the mesh, well, I would say there are very, very few mesh formats that already store the neighbors. Generally, you need to generate such an array. Now, my question to you is, you've got such a mesh. The only thing you know are the coordinates of nodes and the cells stored as connectivity. How do you generate the neighbors array without going into searching everyone with everyone?
Just
think about counting how many times each point appears in the something like that.
What do you mean counting how many times?
For example, in this mesh that we've drawn, the point number 7 appeared 3 times in the cells. And maybe do something with that, with this information.
Would appear even 4 times.
Yeah, 4 times.
Yeah, but what to do with that information?
If 2 points are both in the 2 cell, means that they are neighbors to each other.
Yes, it means that they are neighbors.
I don't think so. No. The second and let's say fifth.
Okay, so like you can go through each, like you can take each node and look in which cells it appears, and then you look between only those cells for the second point.
Okay, so let me rephrase that. What's the naive, stupid way of generating the neighbors array? The stupid way of doing that is the stupid way is loop over cells. Okay, so I'm starting with, let's say, the first cell. Right now, so what I'm interested when I enter the cell, I'm interested what is the neighbor through the first, second, third, and fourth local phase. So what I do is, okay, let's take, let's say we're interested in finding the neighbor through that phase. Okay, so I know that it's constituted by the third and seventh node. So what would I do? So I need to look for the neighbors. So the stupid, naive way would be to again start looping over all cells. 1, 2, 3, etc., etc. And finally, I will find one cell that also has got seventh and third node. Okay? Obviously, if the other cell also is constituted by the seventh and third node, then it needs to be my neighbor through that particular phase. But the problem is that I need to loop over all cells, and then inside each cell, I need to loop over all cells once again. So it's a square algorithm, not very nice if you've got 20 million cells in your mesh. So what's the better approach? The better approach is let's exploit the information about what are good candidates for being a neighbor for me. And good candidates for being a neighbor for me are the cells that already have at least one common node with me. So let's exploit that. To exploit that, To exploit that, I would do the following, namely, already when importing the faces, and remember faces is the array that says something like that. 1, 2, 3, 7, 1, 2, 3, 7, 7, 3, 4, etc. So when already importing, sorry, not faces, cells. So already when importing the cells, I would prepare yet another array. Let's call it cells of a node. Cells of a node would be, okay, we know that, well, how many nodes do we have in our mesh? 11. 1 to 11. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so certainly, what are the cells of the, like when we're importing the first cell, then it's built of the first node, the second node, of the third, and seventh. Right now we know that certainly the first node has got something to do with the first cell, and so on. Like, let's keep looping through that. Okay, second is 2, 2, 2, and so on. Like, this data structure can be generated extremely easily, right? Like during importing the mesh, or when going just in one go, going through that cell, you can generate the information about which cells touch at a given node. So what you do then is when you need to search for neighbors, you loop over all cells, but then when you start looping over the local faces and you want to find the neighbor through that face, then you already know that, okay, so this can only be cells that share third and third and seventh node. So what we would do is we are taking, so we want to see, okay, what are the cells that are built by the third node? What are the cells that are built by the seventh? And let me maybe complete this. At third, we've got 1, 2, 3, 5, 6, and 7. Number 7 is 1, 2, 8, 9. And what you would see is, okay, if I am cell number 1, I need to find what's the intersection of these two sets. And the intersection is, well, 1 and 2 exist in both lists. So if I'm 1, then my neighbor is the second cell. Smart? You have really hugely limited the number of cells that you need to search. You're analyzing that. I can see from your faces. And from your faces, not edges. Okay, so right now let's move to the, we have generated the matrices for the find difference method. Let's see how you can really solve, solve the problem for the find volume method. Can you use find volume method explicitly without any matrices? For the find difference method, we were able to write the explicit or implicit schemes for even for time stepping, upwind central differences, and we were able to write the explicit formula how to calculate the u values at the new time step. Can you do something similar for the find volume method?
Yes, it's supposed to be conservative. We don't know what the fluxes are going to be. So it's implicit by default.
Yeah, but there are some mesh-free methods. So.
No, it's not a mesh-free method because you've got the mesh.
Matrix-free, mesh-free, I don't remember the name. But
Like if you, for sure, if you have non-stationary problem, you can do it.
Yeah.
Just by taking the fluxes from the previous time step.
Exactly.
Creating the explicit Euler method.
Exactly. Let's imagine we want to solve du dt equals diffusion. Okay, and we want to discretize it using find volume method. What would it mean? It would mean that, well, we have some un plus 1, un, our average, divided by delta t, multiplied by the volume of the find volume, equals the diffusion flux, which is minus sum over all phases lambda. Let's assume again lambda is constant, and we need to discretize that. What we would do is u of the neighbor minus my own u divided by distance times the surface area of the face. And the only thing that we need to do is say that our time index is n. This one is known, can be moved to the right-hand side. We've got the explicit formula how to update the u values. You can be time stepping explicitly, exploiting the find volume method.
Can we apply in that place von Neumann stability analysis like we did previously, or it's not suitable for that, or we have to change it? How it goes?
Actually, like for 1D, it reduces to finite difference method.
Yeah, for 1D. For 2D, don't know. I have never tried. But generally, you do have some time step limitation for this one, associated with the diffusivity and the size of the cell. Okay, what would you do if you dealt additionally with the diffusion, with the convection term? We would need to add the convective flux. No wonder. Can you think of the Upwind scheme for the fine volume method explicitly?
Well, just instead of writing the value at the phase, like the average value at the phase, like you take the average value of the Upwind cell.
Exactly. So if we want to write the explicit find volume method and we want to apply the Upwind scheme, then we need to exploit this one in a smart way. In a smart way means if you've got two cells and we want to derive Upwind scheme, this means that you need to check what's the velocity at the phase. If the velocity is like that, so the projection onto the normal is in this direction, then the Upwind scheme for the given phase would be NF times velocity at the given node times, and this UF cannot be computed as some average of my value and the neighbor value, but then, well, let's assume it's me, it's I, is the neighbor. Then for something that is the analog of the central differences would be taking UI plus U neighbor divided by 2 or calculate properly according to the distance if you wish. Taking the Upwind would mean, okay, if the velocity is from the neighbor to my cell, then I need to calculate unit normal vector velocity times U neighbor with absolutely no contribution of the value at my cell times the surface area of the phase. Is okay?
Yeah, the one tricky part is that since we are in, like, for example, Fluent, since we are storing our velocity in the centers also, we need to interpolate it also on the phase.
That's true.
And velocity is contrary to the U, I think linearly interpolated.
Yeah, so basically if you know velocity at your cell and the neighboring cell, what you would do is you would interpolate onto the phase, and you would check whether it's positive or negative, and then you need to take either your neighbor's value of U or your value. But obviously again, it's conservative. It's conservative because once you've calculated the interpolated velocity here, it's either positive or negative. So calculating the incoming flux to your cell is based on your neighbor value, but calculating the, so to say, the flux that leaves the neighboring cell, it's also calculated based on that value. So it's still conservative.